Most people picture the solar system ending at Neptune. 8 planets, a few moons, and then a long quiet darkness. You have seen the diagram. That picture has a problem so severe that once you understand it, the solar system you thought you knew will feel like a first draft. What sits beyond Neptune is a structure more than 1 billion miles wide, containing hundreds of thousands of frozen worlds. We discovered it in 1992. We had been drawing the map of our home for 4 centuries and left out one of its largest features. Tonight we walk through what the Kuiper Belt actually is. The man it was named after, who thought it was already gone. The one spacecraft we sent, and what it found that nobody predicted. If these slow walks through the cosmos help you settle before sleep, a quiet subscribe means a great deal. It helps this channel reach more people who need exactly this kind of quiet. Now, we begin. Close your eyes and picture the solar system. You already know what it looks like. You have seen this image since you were a child. The sun burning at the center. 4 small rocky planets close in. A belt of asteroids between Mars and Jupiter looking like a ring of scattered gravel. Then the gas giants, enormous and ringed, Saturn most dramatically of all. And then Neptune, the last planet, alone at the outer edge. Beyond it, emptiness. The long dark before the next star. You have never questioned this picture. Almost nobody does. But here is what nobody tells you. The diagram you memorized is roughly 50 astronomical units across. 1 astronomical unit is the distance from Earth to the Sun. So, the diagram shows the solar system from the Sun out to about 50 AU. That is where Neptune lives. 30 AU. That is where the diagram ends, at 50. But the solar system does not end at 50 AU. It does not end at 100 AU, the heliosphere, the bubble of solar wind that defines the Sun's influence, extends to roughly 120 AU. Voyager 1, the most distant human-made object, crossed that boundary in 2012. It is now at over 160 AU, and still inside the broader gravitational reach of the Sun. The Oort cloud, the outermost shell of solar system material, extends to roughly 100,000 AU. 100,000. Let that number sit with you for a moment. The diagram you have memorized shows the solar system out to 50 AU. The actual solar system extends to 100,000 AU. The diagram you were given as a child showed you 1/2000th of the real thing. Now hold that picture. The Kuiper Belt sits between 30 and 50 AU, right at the edge of the famous diagram, right where most people assume the solar system trails off into nothing. And it is not nothing. It is a band of frozen worlds more than 1 billion miles wide, containing hundreds of thousands of objects larger than 62 miles across, and millions more smaller ones. It contains at least 5 confirmed dwarf planets. It is the origin point for most of the comets that have crossed Earth's sky throughout human history. We did not know it existed until 1992. That is the first implication worth sitting with tonight. Not the science of the belt itself. The fact that we drew the wrong map. For centuries, astronomers studied the solar system, wrote textbooks about it, sent children home with diagrams of it. And the diagram was fundamentally incomplete. The biggest structure in the inner solar system neighborhood, stretching across 1 billion miles of space, was missing from every picture. If we got the map that wrong about our own home, what else are we missing? That question is not rhetorical. We will come back to it. You probably think the outer solar system is mostly empty, that past Neptune there is a lot of cold and nothing else. Most people do. The diagram suggests it. Even the phrase outer solar system carries a feeling of absence, of distance, of places where things trail off. But here is what makes this genuinely strange. The Kuiper Belt contains more objects than the asteroid belt. by a significant margin, more than 20 times wider, more massive, home to hundreds of thousands of objects larger than a small city. Objects that have been sitting in slow orbits around the Sun since before Earth's continents took their current shapes, before anything on this planet had eyes to see them. Let me make the scale of this concrete. Take the asteroid belt, the famous one between Mars and Jupiter, the one that shows up in every solar system diagram as a ring of scattered rocks. It spans roughly 140 million miles. It contains millions of objects, but its total mass is less than 4% of Earth's moon. It is famous. It is in the diagram. It has its own section in every astronomy textbook. The Kuiper Belt is 20 times wider, much more massive in total, far more populated with large objects. And for most of human history, we simply did not put it in the diagram. Settle in again for a moment, because that is already a strange thing to absorb. The solar system has a major structural feature that we left off the map, not because it is invisible, because we were not looking. Now let us talk about what actually lives out there in that belt of frozen space. At least 5 confirmed dwarf planets: Pluto, which most people have heard of; Eris, which is slightly more massive than Pluto, and which, when it was discovered in 2005, forced astronomy to formally redefine what a planet is; Haumea, which rotates so fast, once every 4 hours, that centrifugal force has stretched it into the shape of a flattened ellipsoid, something like a cosmic rugby ball made of ice, unlike anything else known in the solar system; Make, Quasar, which has a faint ring system sitting at a distance where standard models say a ring should not persist. About 80 known Kuiper Belt objects are binary systems, 2 objects orbiting each other as they orbit the Sun. 2 small worlds locked together by mutual gravity, drifting through the outer dark in a slow embrace that has persisted for billions of years. The belt's total mass is roughly 1 to 10% of Earth's mass. This sounds small, but consider what that means. This is the material that was too spread out, too far from the Sun to coalesce into a proper planet. The building blocks that never finished building. The raw material of a planet that was never assembled, frozen in place at the moment the solar system stopped actively forming. These objects are not rocks exactly. They are mixtures of ice and rock, with surfaces colored red and brown by tholins. Complex organic molecules formed when cosmic radiation acts on frozen methane and nitrogen over billions of years. The redness of the outer solar system is a chemical record of time. Every tint is a year. Every shade is a billion years of slow radiation chemistry in the dark. Take a moment with this. The objects in the Kuiper Belt are not just old. They are archives. Preserved samples of the conditions that existed when the solar system was young. Every rocky planet has been melted, bombarded, differentiated, flooded, and reworked by geology and life. But Kuiper Belt objects have been sitting in the cold since the beginning, almost exactly as they were assembled. They are the solar system's primary record of its own birth, and we have visited exactly one of them up close. 1. Here is something that most people who know the name Kuiper Belt have never been told. Gerard Kuiper, the Dutch-American astronomer whose name is on the belt, published a paper in 1951 speculating about objects beyond Pluto. He was born in 1905 in a small town in the Netherlands, came to the United States in 1933, and spent much of his career at the University of Chicago and the University of Arizona. He was one of the founding figures of modern planetary science. Craters on the Moon and on Mercury bear his name. The Airborne Observatory NASA operated for 2 decades was named after him. In that 1951 paper, Kuiper proposed a region of outer solar system objects. His name went on to the region. He is celebrated as the person who predicted its existence. But here is what that paper actually said. Kuiper believed that Pluto, which in 1951 was thought to be significantly larger than we later discovered, had already swept through the outer region and scattered most of the icy objects outward. In Kuiper's model, the belt had existed once and had since been cleared out. He was proposing a region that he believed no longer existed in any meaningful sense. He put his name on an empty room. This is one of the quieter ironies in the history of science. A man proposes a region, argues it has already been destroyed, and then has the region named after him when it turns out to be full of millions of objects. An Irish astronomer named Kenneth Edgeworth had raised similar ideas in 1943, 8 years before Kuiper's paper. Edgeworth was born in 1880, served as a British Army officer before turning to theoretical astronomy, and spent much of his later career publishing work in relative obscurity that was decades ahead of its time. He argued that the outer solar system contained a large number of comparatively small bodies, objects that never managed to coalesce into a planet because the material was too spread out and the orbital periods too long. Some astronomers today use the name Edgeworth-Kuiper Belt to give him the credit he earned. Both men pointed at the same dark region. Neither had the instruments to confirm it. Neither lived to see it confirmed. In 1980, Julio Fernandez, a Uruguayan astronomer working at the Astronomical Observatory of Montevideo, published a paper in the monthly notices of the Royal Astronomical Society making a specific quantitative prediction. He argued that a belt of objects beyond Neptune was the source of the short-period comets observed in the inner solar system. His math required the belt to contain a minimum number of objects to supply comets at the observed rate. He gave the field a concrete target. His work is often cited as the paper that made the Kuiper Belt's existence a serious scientific prediction rather than a qualitative speculation. Edgeworth in 1943, Kuiper in 1951, Fernandez in 1980. 3 different people, 3 different decades, 3 different countries, all pointing at the same dark region of space. None of them could confirm it. The tools did not yet exist, and then someone found the patience to actually look. In 1987, David Jewitt was working at MIT and feeling what he would later describe as a professional unease. Jewitt, who had completed his doctorate at Caltech in 1983 and was building a reputation as one of the most careful observational astronomers of his generation, had been thinking about the outer solar system for years. The theoretical case for some population of trans-Neptunian objects had been building since at least the 1940s. But nobody had found anything. The surveys that existed were not deep enough, not systematic enough, not patient enough. Jewitt began a systematic search. He worked with a graduate student named Jane Liu, who had been born in Vietnam in 1963, immigrated to the United States as a teenager following the fall of Saigon, and was completing her graduate work at MIT. She would later hold positions at Harvard, MIT, and the European Southern Observatory, and would share a major astronomical prize with Jewitt for this work in 2012. Together, they used telescopes at Kitt Peak National Observatory in Arizona and the Cerro Tololo Inter-American Observatory in Chile. The method was systematic and exhausting. Photograph the same patch of sky twice in a single night, hours apart. Then compare the 2 images with painstaking attention. Stars stay fixed. An object orbiting the sun moves. The movement appears as a tiny shift in position between the 2 images. They searched for 5 years. 5 years of telescope nights. 5 years of photographic comparisons. 5 years of finding nothing that was not already catalogued. The outer solar system kept returning the same answer. Nothing here. Sit with that for a moment. 5 years. Edgeworth, Kuiper, and Fernandez had collectively spent decades arguing that something was out there. and the only way to prove it was to point instruments at empty sky night after night and refuse to stop. Then, on the night of August 30th, 1992, on the summit of Mauna Kea in Hawaii, Jewitt and Liu compared two images taken 15 minutes apart. They were examining a field of sky in the constellation Sagittarius. A faint point of light had shifted, a tiny amount, a measurable, precise, orbital amount. Jewitt said later, simply, "We both fell silent." The object was eventually named Albion. For years, it was called only 1992 QB1, the alphanumeric label assigned to new solar system objects in sequence. A chunk of ice and rock roughly 250 kilometers across, orbiting the Sun at about 44 astronomical units on a path that takes roughly 3 centuries to complete. Small, cold, dark, slow, but real. And there, in the months and years after 1992 QB1, the detections multiplied. Dozens, then hundreds, then thousands, until the population was too large, too structured, too clearly organized by the physics of the outer solar system to be anything other than what Edgeworth had imagined in 1943. The solar system had a third zone. It had always had one. And once we knew where to look, it was everywhere. Now hold that thought, because knowing the zone existed was only the beginning. What we have done, and not done, with that knowledge since 1992 is where the story gets genuinely strange. In the entire history of space exploration, we have sent exactly one spacecraft to study the Kuiper Belt up close. 1. Let that number sit with you for a moment against everything else we know about the belt. Hundreds of thousands of large objects, millions of smaller ones, at least 5 dwarf planets, 1 billion miles of territory, a primary source of Earth's comets, the most pristine archive of early solar system material anywhere in our neighborhood, ancient, vast, scientifically irreplaceable. 1 spacecraft. New Horizons launched on January 19, 2006 from Cape Canaveral. It left Earth moving faster than any spacecraft before it, fast enough to pass the Moon's orbit in 9 hours, a journey that took the Apollo crews 3 days. It received a gravity assist from Jupiter in February 2007 that added more speed and shaved years from the journey. And then it flew, quietly. For 9 years, the mission was led by Alan Stern, a planetary scientist at the Southwest Research Institute in Boulder, Colorado. Stern had spent much of the previous decade fighting for a Pluto mission in an era where NASA's priorities lay elsewhere. Multiple proposals were made, multiple proposals were cancelled. When New Horizons finally received funding and a launch date, it did so just barely in time to make use of the Jupiter Assist window. A later departure would have added several years to the journey and required more fuel than the spacecraft could carry. For 9 years, New Horizons was mostly dormant. It transmitted a weekly status signal. Occasionally it woke for calibrations. 9 years is a long time to wait for a flyby that would last only hours. On July 14, 2015, New Horizons passed within about 7,750 miles of Pluto's surface. The encounter lasted hours. It was a flyby, a single pass through the system at high speed, with every instrument recording everything it could in the brief window. The data took 16 months to fully transmit back across 3 billion miles of space at the slow rate that distance allows. What arrived overturned decades of assumptions. Pluto had mountains, towers of water ice as tall as the Rockies, standing on a surface where the temperature hovers around 30-80 degrees below 0 Fahrenheit. At that temperature, water ice has the hardness of granite. Those mountains had been standing undisturbed for an unknown span of time. It had glaciers of frozen nitrogen flowing across the surface in convective patterns, despite the temperature being cold enough to liquefy oxygen. It had a heart-shaped plain, unofficially named Tombaugh Regio, after Clyde Tombaugh, who found Pluto in 1930. The plain is covered in relatively fresh nitrogen ice, young by geological standards, suggesting active geological processes on Pluto's surface after 4-5 billion years. And beneath all the ice, the data pointed toward a liquid water ocean, kept from freezing by heat generated by radioactive decay in Pluto's rocky core. Pluto, the symbol of cold, distance, and desolation, appears to likely have liquid water inside it right now. Let your shoulders drop for a moment and think about what that means. We sent one spacecraft to the Kuiper Belt. That spacecraft flew past one object for a few hours, and it found an active geological world with liquid water beneath its surface. In the first object we ever looked at closely in the Kuiper Belt. And after Pluto, New Horizons kept going. After the Pluto flyby, New Horizons had enough remaining fuel and power to reach a second target. The Hubble Space Telescope conducted a dedicated search along the spacecraft's outbound trajectory in 2014. It found a candidate. A small, faint, reddish object at roughly 44 astronomical units from the Sun, almost perfectly positioned along New Horizons' path. The object was eventually named Arrokoth, from the Powhatan and Algonquian word for sky. New Horizons flew past Arrokoth on January 1, 2009. At 43.4 astronomical units from the Sun, Arrokoth became the most distant object ever explored up close by any spacecraft in history. The images came back slowly, as they always do at that distance, and what they showed was immediately strange. Arrokoth is a contact binary, 2 lobes, a larger one called Wenu, a smaller one called Wio, pressed gently against each other. Not the result of a violent collision. The data showed that the 2 lobes had once been a binary pair orbiting each other as they orbited the Sun, gradually losing energy over millions of years through a process called dynamical friction, until their orbits decayed and they touched. At a relative speed of perhaps a few miles per hour, a settling, a coming together. Arrokoth's surface is smooth and largely uncracked. This was the key observation. Objects with significant collision histories accumulate damage, craters, fractures, irregular surfaces. Arrokoth has almost none of this. Its surface is pristine in a way that tells a specific story. It was assembled gently, from material that gathered under its own gravity without high-speed impacts. This matters enormously, not just for Arrokoth, for everything. The leading explanation for Arrokoth's formation is gravitational instability, a cloud of pebble-sized material that was slightly denser than its surroundings, slowly collapsing inward under its own weak gravity. No violent collisions, no catastrophic impacts. Just a slow gathering of material into the configuration we found 4-5 billion years later. 2 lobes drifting together like something that had always been going to meet. If Arrokoth formed this way, then the standard model of how planetesimals form, the building blocks of planets, the first solid objects in the early solar system, was wrong, or at least incomplete. The standard model assumed that planetesimals grew through violent collisions. Small objects hitting each other and sticking. Gradual accumulation through impact. Arrokoth suggests something quieter, more patient, more gentle than anyone predicted. Now think about what this implies for the inner solar system. If the outer solar system formed gently, the inner solar system may have too. Earth, Mars, the rocky planets we live with. Their building blocks may have assembled through the same quiet process we found preserved in Arakoth's shape. We found a record of how planets are born, frozen into one small world in the outer dark, waiting for 5 billion years for something to fly past and notice. Picture Arakoth from a few hundred kilometers away. It is 35 kilometers long, roughly the distance from one end of a major city to the other. Its surface is reddish from tholins. The two lobes are joined at a smooth seam. No crater at the join, no sign of impact. The sun from there is a bright star in a sky full of stars, none of which are close enough to matter. In that absolute cold, in that absolute quiet, Arakoth has been drifting on its 3-century orbit since before anything on Earth had a spine. It waited in the dark until we sent something to find it. We flew past it once, for a few hours. You have probably seen a comet, or seen a photograph of one, the bright nucleus trailing a long, pale tail across the sky. Ancient civilizations took them as omens. The Babylonians recorded them in 240 BC. The Norman conquest of 1066 appears in the Bayeux tapestry with Halley's comet blazing overhead. Here is what nobody in those civilizations knew, and what we know now. Most of the short-period comets that have crossed Earth's sky throughout human history, those with orbital periods under 200 years, the ones that return on human timescales, originated in the Kuiper Belt. To understand what that actually means, consider how the mechanism works. Kuiper Belt objects orbit the Sun in stable, near-circular paths. Most have been in those paths for billions of years, undisturbed. But Neptune orbits at the inner edge of the belt. Neptune is 17 times the mass of Earth. Its gravity extends well into the belt's territory and establishes resonances, orbital configurations, where a belt object completes a precise number of orbits for every orbit Neptune makes. A 2003 resonance means the object completes 2 orbits for every 3 Neptune completes. Pluto itself is in a 2003 resonance with Neptune. This is why Pluto has survived in the belt without being ejected over billions of years. The resonance is stabilizing, but resonances can also be destabilizing. Objects that wander into certain unstable configurations get nudged on each pass. The nudges are small individually. They accumulate over millions of years. The orbit becomes more elongated, more eccentric. The object begins dipping inward toward the inner solar system on each approach to the Sun. As it approaches the Sun for the first time in billions of years, the outer layers of ice begin to sublimate. Water, carbon dioxide, carbon monoxide, methane, frozen gases transforming directly from solid to vapor and streaming outward from the nucleus. Dust and larger particles escape with the gas. The tail forms, always pointing away from the Sun regardless of the direction of travel, because solar wind pushes it. The comet is born. The comet that an ancient Babylonian astronomer recorded. The comet that frightened medieval populations and was painted into tapestries. The comet that schoolchildren see in photographs. That object has been a Kuiper Belt object for 5 billion years. It has been cold and dark and motionless in orbital terms, completing slow circuits around the Sun. And then Neptune's gravity sent it falling inward. And for the first time since the solar system formed, it entered the warmth and became briefly visible. Halley's comet, with its 75-year orbital period, almost certainly originated in the Kuiper Belt or the adjacent scattered disk. Now take a moment with this. The comet is not a visitor from somewhere else. It is from here, from the same cloud of material that formed the Earth. It sat in the cold for 4 billion years, and then it fell inward. Not a visitor from outside. A piece of the original solar system, returning from the deep cold to briefly pass through the warmth. But there is a deeper implication. Comets that reach Earth do not just pass by, they interact. Cometary material analyzed from spacecraft encounters and from meteorites that appear to be cometary in origin contains organic molecules, amino acids, complex carbon compounds, the chemical precursors to the building blocks of life. Whether any of this material contributed meaningfully to the chemistry of early Earth is actively debated and not yet conclusively established. The Kuiper Belt has been in slow, intermittent communication with the inner solar system for billions of years, sending material inward, delivering parcels of the outer solar system to the inner one. The atoms in your body may have spent time in the Kuiper Belt. There is no way to be certain they did not. A quiet note before we continue. If this kind of slow, careful exploration is what brings you here, a quiet like or subscribe means a lot. It helps this channel find more people who would love it. Thank you. Now, there is one more thing the Kuiper Belt has been doing quietly for billions of years. And it is something we have only just noticed. If you plot the distribution of Kuiper Belt objects against their distance from the Sun, a strange feature appears in the data around 48 to 50 astronomical units. The population, which has been reasonably dense through the belt's main region, drops. Not gradually, not as a slow fade, it falls off a cliff. Astronomers call this the Kuiper Cliff. That sounds technical, so let me make it concrete. Imagine watching a city from the air as you fly further and further away from its center. Downtown buildings, then suburbs, then outer neighborhoods thinning as countryside begins. That is the gradual fade you would expect from a city following normal population density patterns. That is also the gradual fade that solar system formation models predict for the Kuiper Belt. What astronomers actually observe is more like flying away from that city and then, at one specific street, finding that every building simply stops. Not fades. Stops. A sharp line where populated space ends and emptiness begins. No suburb, no exurb, no gradual trailing off. A wall. That wall should not be there. Standard solar system formation models. Models tested against dozens of other observations and considered robust by planetary scientists do not predict a sharp edge at 50 AU. They predict a gradual decline. The Kuiper Cliff is not in any of the models. It appeared in the data, and nobody had a ready explanation. Several explanations have been proposed. One invokes a massive planetary body that may have existed in the early solar system and has since been ejected. A world large enough to sweep the outer belt nearly clear during the chaotic period of planetary rearrangement 4 billion years ago, leaving the sharp outer boundary we observe today. Another points to Neptune's outward migration during the same early period. As Neptune moved outward, its gravitational resonances swept through the outer solar system like a slow broom, clearing and compressing the belt. The Nice model, named after the city in France where the theoretical framework was developed, describes this early period of planetary rearrangement. Neptune's migration in the Nice model could potentially explain a belt with a sharp outer edge, but the models have not yet produced a cliff as sharp as what the surveys find. A third explanation suggests the cliff reflects the outer boundary of where the original solar nebula, the cloud of gas and dust that formed the solar system, was dense enough to form solid objects. The raw material simply ran out at approximately 50 AU. The belt ends there because there was nothing to start with further out. None of these explanations has definitively won. Each makes predictions that the data partially supports and partially complicates. The Kuiper Cliff is, as of 2026, one of the genuine, open problems in outer solar system science. It may be one of the most important, because whatever caused it is almost certainly tied to the earliest history of the solar system, to the violent, chaotic period a few 100 million years after formation, when everything was still rearranging itself. And here is what makes this genuinely strange. For a long time, the reasonable assumption was that the drop in detected objects at 50 AU reflected a real drop in the population, that the Kuiper Belt genuinely ended there, that the cliff was the edge. Then a spacecraft that had already flown past the cliff sent back data that made that assumption very difficult to hold. New Horizons carries an instrument called the Venetia Burney Student Dust Counter. The name comes from Venetia Burney, who was 11 years old in 1930 when she suggested the name Pluto for the newly discovered world at breakfast with her grandfather, Falconer Maydan, a retired librarian at the Bodleian Library at Oxford. Her grandfather passed the suggestion to an astronomer he knew at the Lowell Observatory. The astronomers adopted it. Venetia Burney lived to see New Horizons launch in 2006, carrying her name to the outer solar system. She died in 2009, 6 years before New Horizons reached Pluto. The student dust counter measures the impacts of microscopic dust particles against its surface as the spacecraft moves through space. Now, let me explain why this matters, step by step. Dust in the outer solar system is produced by collisions. When two Kuiper Belt objects strike each other, even at the relatively gentle speeds of belt collisions, they produce debris at all scales. Fragments, pebbles, dust particles a few microns across. This debris spreads through the surrounding space. The density of dust in any region reflects, roughly, the density of objects producing it. More objects, more collisions, more dust. Here is what this means. In practical terms, if the Kuiper Belt ends at 50 AU, the dust production ends at 50 AU. Beyond the cliff, there are no belt objects. No objects means no collisions. No collisions means no dust. So as New Horizons flew past 50 AU and into the region beyond the cliff, the student dust counter should have recorded a falling impact rate. It did not. Between 45 and 60 astronomical units, the student dust counter kept recording dust impacts at rates inconsistent with an empty region, not declining. In some stretches, elevated relative to what the models predicted even within the known belt. Alan Stern, the mission's principal investigator, reported on this in April 2024. His language was precise. The number of impacts is not declining, he said. The simplest explanation is that there is more material out there that we have not yet detected. More material. Beyond where the belt was supposed to end. The physics here is unambiguous. You cannot have dust without collisions. You cannot have collisions without objects. The student dust counter was not designed to answer the question of whether a second belt existed. It was designed to measure dust. But the dust was answering the question anyway. Something was out there, past the cliff, in the region the old maps marked as empty. Something was colliding. Something was producing debris. And New Horizons was flying through that debris and recording it. Think about how this discovery happened. Not through dramatic telescope observation, not through a new survey, through a small instrument on a spacecraft counting the faint tick of microscopic particles against its surface, past 50 AU where the belt was supposed to have ended, registering impacts that should not have been there. The cosmos revealing itself through the quietest possible measurement. Dust. The map we drew ends at 50 AU. The universe does not. At roughly the same time, a separate line of evidence was converging on the same conclusion from the ground. The Hypersuprime Cam is a wide-field camera mounted on the Subaru telescope, an 2-meter instrument operated by the National Astronomical Observatory of Japan on the summit of Mauna Kea in Hawaii. Starting in 2020, a team of astronomers began using it to search along New Horizons' projected outbound trajectory. The primary goal was to find potential future targets for the spacecraft. The survey discovered 239 Kuiper Belt objects in the known belt region between 30 and 55 astronomical units. Significant in its own right. But the more striking result was at greater distances. Among the objects discovered, 11 were located beyond 60 astronomical units beyond the Kuiper Cliff, in the region where, by the old models, there should be almost nothing. 11 objects is a small number, but statistics is clear on the implications. The Subaru survey examined a narrow slice of sky, a specific corridor along New Horizons' path. If 11 objects appeared in that narrow slice at distances beyond 60 AU, the total population across the full sky at those distances is vastly larger. These 11 are almost certainly the edge of a much larger population. The tip of an iceberg. Fumi Yoshida of Chiba Institute of Technology in Japan, a team member on the survey, described the result as the most exciting finding of the entire campaign. 2 scientific papers were published in the Planetary Science Journal in 2024 presenting the data. The orbits of the 11 objects are still being tracked and refined. As of 2026, the research is ongoing. Alan Stern described the combined evidence. Dust counter data from New Horizons plus the Subaru telescope discoveries as a groundbreaking discovery. He noted that this may be the first time a spacecraft has discovered evidence for a new population of solar system bodies, independently confirmed by ground-based telescope surveys. Now hold that picture. One spacecraft measuring dust that should not exist. One telescope finding objects that should not be there. Both pointing at the same conclusion. The solar system has more to it than the maps showed. Something exists beyond the Kuiper Cliff, something we had not charted, something we had not even strongly suspected until a few years ago. Whether this represents an extended Kuiper Belt, the same belt simply reaching further than previously mapped, or a genuinely distinct second structure at greater distances is still being debated. The 2 possibilities have different implications for how the solar system formed. A continuous extended belt suggests the solar nebula reached further than we thought. A distinct second belt requires a different formation story entirely. Perhaps a population of objects scattered outward during the early chaotic period, settling into a stable configuration that has persisted ever since. The data does not yet distinguish clearly between them. What is clear is that the map was wrong again. In the same way and in the same place, it was wrong before 1992 by leaving out something real. And then there is Planet 9. In 2016, Konstantin Batygin and Mike Brown published a paper that made a quiet argument with large implications. Batygin had completed his PhD at Caltech in 2012 and was known for applying rigorous mathematical analysis to problems others had addressed, mainly qualitatively. Brown was the same astronomer who had found Eris in 2005, the discovery that led directly to Pluto's reclassification as a dwarf planet. Together they examined the orbital properties of a handful of distant Kuiper Belt objects, those with large, elongated orbits that swung far out into the outer solar system before looping back in. They noticed something in the data that did not look random. 6 of the most distant known objects were clustered. Their orbits were tilted and oriented in space, such that they pointed toward the same general region of sky. Statistical analysis put the probability of this alignment arising by chance at less than 1 in 10,000. Their interpretation was that the clustering was not random. A massive body on a distant orbit was gravitationally shepherding these objects into the aligned configuration. The way a planet sculpts the neighborhood around it, but operating over vast distances and orbital timescales measured in thousands of years. This body would need to be roughly 5 to 10 times the mass of Earth. on a highly elongated orbit, taking it from perhaps 200 to 1,200 astronomical units from the Sun, completing one orbit every 10,000 to 20,000 years. Planet 9. The hypothesis generated immediate and substantial scientific pushback. Several teams examined the same observational data and argued that the apparent clustering was an artifact of selection bias. Astronomers do not search for distant outer solar system objects uniformly across the full sky. They concentrate their surveys in regions most accessible from major observatories, with the most telescope time available, with the least interference from the dense star fields of the Milky Way. Objects in the most surveyed regions get found. Objects in the less surveyed regions do not. The clustering in the data, critics argued, reflected the pattern of the surveys rather than any real gravitational influence. This is a genuine scientific dispute. As of 2026, Planet 9 has not been detected by any telescope. Its existence remains a hypothesis. The Vera Rubin Observatory, also called the Simonyi Survey Telescope, conducting the Legacy Survey of Space and Time, is expected to begin full operations in the coming years. Its 10-year planned survey of the southern sky will be the deepest and most comprehensive survey of the outer solar system ever conducted. If Planet 9 exists at the parameters Batygin and Brown proposed, Vera Rubin should find it. If it does not appear, the hypothesis will need substantial revision or abandonment. But here is what makes this genuinely strange to sit with. If Planet 9 exists, it is almost certainly a former giant planet of the early solar system, ejected outward during the chaotic period of planetary rearrangement that reshaped everything 4 billion years ago, a world that formed close to the Sun, possibly between the orbits of Jupiter and Saturn, and was flung outward by gravitational interactions until it settled into its current enormous orbit. A planet that has been out there, in total darkness, completing orbits so slow that it has made only a few hundred of them since the solar system formed. Unseen, undetected, shaping the orbits of distant belt objects through gravity alone. If it exists, it is the largest thing in the solar system we have never seen. And if it does not exist, then the orbital clustering has some other explanation we have not yet identified. Either way, something is happening in the outer solar system that our models do not fully account for. The honest answer is, we do not know. That answer is uncomfortable. We are used to the solar system being mapped. We are used to the planets being counted. The idea that there might be a planet-sized object in our own solar system that we have simply never found goes against the sense of completeness we have built up over centuries of observation. But that sense of completeness was always an artifact of limited instruments, not a reflection of actual knowledge. We did not find the Kuiper Belt until 1992. We may not have found everything in the solar system yet. Here is where we need to stop and sit with the implications directly. You probably think the well-explored regions of the solar system are extensive. We have visited Mars. We have landed on the Moon. We have sent probes to Jupiter and Saturn. We have flyby data from every planet. Surely we have a comprehensive picture. But here is what nobody tells you about space exploration. The Kuiper Belt begins at 30 AU and extends to at least 50 AU and possibly to 80 or 100 AU or beyond. In that entire region, the largest single structural feature of the solar system we know of, spanning billions of miles, containing hundreds of thousands of large objects and millions of smaller ones. We have sent one spacecraft. One. New Horizons was launched in 2006. It reached Pluto in 2015. 9 years of flight for a flyby that lasted hours. It then flew to Arrokoth in 2009. another flyby of ours. The spacecraft is still operational as of 2026, now past 60 AU, its power declining slowly. When its power finally fails, it will continue flying outward, silent, into interstellar space. No return. A single pass through one of the largest regions in the solar system, and then gone. Now, let me take the three-step escalation this topic demands. At the basic level, we have a gap in our knowledge. The Kuiper Belt is understudied relative to its scientific importance. This is a resource allocation problem. Scientists know it. They write proposals for new missions. Some eventually get funded. This is how science works. Gaps close slowly. At the moderate level, the gap is not just about resource allocation. It is about what we do not know that we do not know. When New Horizons flew past Pluto, it found mountains, glaciers, and liquid water that nobody had predicted. Not because planetary scientists were bad at their jobs, because Pluto was essentially unobserved before the flyby. Our models of what Pluto should look like were built on indirect data and theoretical assumptions. Reality was dramatically different. We did not know we were wrong until we looked. The Kuiper Belt has hundreds of thousands of objects. Our models of what those objects should look like are built on the same kind of indirect data and theoretical assumptions that produced our wrong picture of Pluto. Every single one of those objects could be dramatically different from what we predict. We have no way to know. We are not looking. At the extreme level, this is not just about the Kuiper Belt. The Kuiper Belt is the best known outer solar system structure, and we have sent one spacecraft to it. The scattered disk, which overlaps the outer Kuiper Belt and extends far beyond it, has had no dedicated missions. The inner Oort cloud, theorized to contain trillions of objects, has never been directly detected. The outer Oort cloud has never been visited. Sedna, a distant planetoid orbiting at up to 900 AU, has been observed only telescopically. There are objects in the outer solar system we know exist and have not visited. There are almost certainly objects we do not know exist. The solar system is not mapped. We have a diagram. The diagram is incomplete in ways we cannot fully quantify because we do not know what we are missing. Now compare this to what we have sent to Mars. More than 50 missions, multiple rovers, plans for human landings, sustained, decades-long investment. Mars is 5 AU from the Sun. The Kuiper Belt is 30 to 100 AU from the Sun. The Kuiper Belt is harder to reach. That is part of the explanation, but only part. The other part is the time scale. Missions to the Kuiper Belt operate on time scales that exceed political cycles. You propose a mission. It gets studied for years. It gets funded after years of advocacy. It launches. It flies for 9 years. It returns data for months. The entire process takes 2 to 3 decades. The politician who funded it is retired before the data arrives. The scientist who proposed it may be dead. We are not built for this kind of patience, institutionally. We are built for quarterly reports, election cycles, budget years. The outer solar system operates on timescales measured in decades and centuries and billions of years. Bridging that gap requires a specific kind of institutional will that we have not consistently demonstrated. Settle in for a moment. Because this is the thing about the Kuiper Belt that is actually uncomfortable, you probably expected this section earlier. You probably expected the horror to be about the scale of the belt, or the danger of incoming comets, or the sheer coldness of the outer solar system. And yes, those things are real, but they are not the horrifying reality this title is pointing at. The horrifying reality is simpler, and it is about us. Here is what we know as of 2026. The Kuiper Belt exists and is enormous. We have known this for 34 years. We have sent one spacecraft to it. That spacecraft returned discoveries that rewrote the theory of how planets are built, found active geology and liquid water on a world we had assumed was dead, and detected evidence of a previously unknown outer region. And we have no follow-on missions currently in active development with a confirmed launch date. Let that sit with you. After one of the most scientifically productive space missions of the modern era, we have no successor mission on track. Think about what that means for everything we discussed tonight. The Kuiper Cliff is unexplained. We have not sent anything to map it in detail. The dust counts beyond 50 AU. Suggests something out there we had not charted. We have not sent anything to investigate. The 11 Subaru telescope objects beyond 60 AU are being tracked telescopically, but have not been visited. Planet 9 may or may not exist, and we are relying on a ground-based survey rather than a spacecraft to tell us. In every case, the limitation is the same. Not physics, not technology. Priority. Here is a comparison. The asteroid belt was discovered in 1801. By 190 years later, we had flown past several asteroids and landed on one. The Kuiper Belt was discovered in 1992. 34 years later, we have flown past 2 objects. 2. This is not because the Kuiper Belt is unimportant. It is because the Kuiper Belt is far. And far means slow. And slow means that the people who make funding decisions today will not be around to see the results. And that creates a structural disadvantage that the Kuiper Belt has never overcome. Now think about what we are actually choosing when we choose not to fund missions to the outer solar system. We are choosing not to find out what the hundreds of thousands of large Kuiper Belt objects actually look like up close. We are choosing to leave the Kuiper Cliff unexplained for longer. We are choosing not to confirm or rule out the possible second belt beyond 50 AU with spacecraft data. We are choosing not to resolve the Planet 9 question with direct detection. We are choosing to leave the most pristine archive of early solar system material in our neighborhood unexamined. These are not passive choices. They are active choices. Every budget cycle in which the Kuiper Belt does not receive a follow-on mission is a choice to learn less about our solar system than we could. The horrifying reality is not that the Kuiper Belt is dark and cold and vast. The horrifying reality is that we know it is dark and cold and vast, and we know it contains scientifically irreplaceable material. And we know that every flyby we have done has returned discoveries nobody predicted. And we are still not consistently prioritizing going back. We are the first generation in history to know the Kuiper Belt exists. We are the generation that has the technology to explore it. We are choosing largely not to. That is uncomfortable, and it is worth being uncomfortable with. But this is not where the story ends, because the story is not finished. The Vera Rubin Observatory will begin its full sky survey in the coming years. It is expected to discover tens of thousands of new Kuiper Belt objects. It may trace the structure of the possible second belt. It may resolve the Planet 9 question. It will dramatically expand our understanding of the outer solar system without sending a single spacecraft. And beyond Vera Rubin, proposals for outer solar system missions continue to be made. The scientific community has not stopped advocating. The case for a dedicated Kuiper Belt orbiter is being made. The case for returning to Pluto for orbiting rather than flying past is being made. The instruments are being proposed. The science is being developed. The outer solar system is patient. It has time. The question is whether we do. So, as you settle into the quiet of this evening, perhaps carry one final thought with you. The edge of the solar system is not a wall. It is not a place where space runs out. It is not a line someone drew that the universe honors. It is a question. A question that keeps moving outward every time we build an instrument sensitive enough to ask it. In 1930, the solar system ended at Pluto. In 1992, we found the Kuiper Belt. In 2015, we found active geology and possible liquid water in the first Kuiper Belt object we ever looked at closely. In 2023, we found evidence of material beyond the supposed edge of the belt. Every time we looked more carefully, the boundary moved. The solar system is not done revealing itself. The silence above tonight is not emptiness. The cold is not absence. The dark is not stillness. Out there, in orbits that take centuries to complete, hundreds of thousands of frozen worlds are moving through the dark. Some have moons. Some have ring systems that should not be stable by our current models. Some may have liquid interiors we have not detected. Some are archives of the moment the solar system began, preserved almost exactly as they were assembled, 4-5 billion years ago. And somewhere beyond the cliff at 50 AU, something is moving too, something we have detected only through the dust it leaves behind, something our current maps do not yet name. The Kuiper Belt is asking something of us, not admiration. It does not need to be appreciated. It has been there since before anything on Earth had a nervous system, and it will be there long after we are gone. What it is asking, in the quiet way that science asks things, is the willingness to sustain attention over decades, to fund missions whose results will not arrive within any political cycle, to train scientists who will spend their careers on questions that will not be resolved in their lifetimes, to be the kind of civilization that thinks on the timescale the solar system actually operates on. That is not a small ask. But consider what it returns. Every time we have looked more carefully at the outer solar system, we found something we did not predict. Every time we sent a spacecraft, we came back with discoveries that changed our models. The Kuiper Belt is not withholding its secrets, it is offering them to anyone who looks. The secrets are just in a place that requires sustained commitment to reach, and perhaps the deepest thing to hold on to as you drift towards sleep tonight is this. We live in a solar system we do not fully know. The map we carry in our heads, 8 planets, a few moons, and then emptiness, is a rough sketch of a territory so large and so varied that we have spent 4 centuries exploring it and still know only a fraction of what is there. The Kuiper Belt is one of the largest features we have found. We found it 34 years ago. We have sent one spacecraft, and that one spacecraft found things nobody predicted in every object it visited on every instrument it carried. The darkness beyond Neptune is not empty. The cold is not absence. The silence is not stillness. It is patient. And somewhere out there, in an orbit we have not mapped, in a distance we have not visited, something is moving through the dark that does not yet have a name, in a solar system that has not yet finished showing us what it. Here is a comparison that makes the one spacecraft problem concrete in a way that is hard to dismiss. In 1969, 12 human beings walked on the moon. Since 1972, none have. That is more than 50 years without a human on the moon. We have since sent rovers, orbiters, and landers, dozens of robotic missions. We know the moon far better than we did in 1972, but no human has walked on it in over 50 years. The moon is 3 days away. The Kuiper Belt is 9 years away with the fastest spacecraft we have built. And we have sent one, and it was not designed to orbit or land or conduct extended study. It was designed to fly past at high speed and collect what it could in the hours it had. Now think about what 9 years means for mission planning. If you propose a Kuiper Belt mission today, a serious proposal with a team, a budget estimate, a scientific justification. It would need to survive the proposal process, get funded, go through development launch, and then fly for 9 years before returning its first major results. You are looking at 2040 or later for data from a mission proposed and funded now. The people who would receive that data are currently in high school. The scientists who would analyze it are currently undergraduates. The people making the funding decisions right now will be retired by the time the results come in. This is the fundamental structural problem of outer solar system exploration. It does not fit the timescales on which modern institutions operate. It is not that outer solar system science is unimportant, or that scientists do not want to do it. It is that the return on investment is real, but deferred by decades, and institutions are not generally good at investing for decades. Deferred returns. The scientists who championed New Horizons, Alan Stern most visibly, but many others, spent years fighting for a mission that was cancelled twice before it was finally approved and funded. Years against competing priorities, against budget pressures, against the argument that there were more immediate targets. They won eventually. New Horizons got funded. It launched. It arrived. It returned discoveries that nobody had predicted and that rewrote multiple areas of planetary science. And then it got past Pluto, and we did not fund a follow-on mission. That is the arc we are in. A mission wins a multi-decade fight for funding, returns extraordinary results. And the extraordinary results are not sufficient to immediately produce a successor mission, because the extraordinary results arrived in a world with different budget priorities than the world in which the mission was proposed. Take a moment with that, not as a critique of any particular decision, as a description of the gap between the timescales on which the outer solar system operates and the timescales on which we make decisions. The Kuiper Belt will still be there in 100 years, unchanged, patient. The only thing that changes with time is our ability to understand it. And right now, that ability is limited by priorities that had nothing to do with what is out there. Here is the deepest layer of the horrifying reality. It is not just that we have sent one spacecraft. It is that every time we have sent a spacecraft to a place we have never closely observed before, we have found something our models did not predict. Not sometimes, every time. Voyager 1 and Voyager 2, launched in 1977, flew past Jupiter, Saturn, Uranus, and Neptune. At every planet, they found things that surprised the scientific community. Active volcanoes on Io, which nobody had predicted. A braided ring structure at Uranus. A great dark spot on Neptune. A geologically active surface on Triton, Neptune's largest moon, with geysers erupting nitrogen gas into the thin atmosphere. Every flyby surprises. Cassini, which orbited Saturn from 2004 to 2017, found an ocean of liquid water under the ice of Enceladus, with hydrothermal activity on the ocean floor. It found lakes of liquid methane on Titan. It found a hexagonal storm system at Saturn's North Pole, with no clear precedent in solar system science. These were not minor refinements to existing models. They were fundamental discoveries that none of the pre-mission models had confidently predicted. New Horizons found mountains on Pluto, liquid water under its ice, and geological activity after 4-5 billion years. The pattern is so consistent that it is essentially a law at this point. Go somewhere new in the solar system, look carefully, and you will find something you did not expect. The solar system is more varied, more active, and more geologically complex than our models predict, at every scale and at every distance from the Sun. Now hold that thought against the Kuiper Belt. The Kuiper Belt has hundreds of thousands of large objects. We have looked carefully at two of them, Pluto and Arrokoth. Both contained major surprises that revised significant areas of planetary science. Assuming the pattern holds, and there is no reason to think it will not, every large Kuiper Belt object we visit carefully will contain something our models do not predict. We have visited 2. There are hundreds of thousands. The scientific content sitting out there in the Kuiper Belt, waiting to be discovered, is not a minor supplement to our knowledge of the solar system. It is potentially transformative. Every object is a frozen archive of early solar system conditions. Every binary system tells us something about how material aggregates in the outer solar system. Every geological feature is a clue to internal processes we do not yet understand. Every unexpected discovery, and there will be many unexpected discoveries, will revise some part of our understanding of how the solar system formed and evolved, and most of it will not be visited in our lifetimes. Not because it is impossible to visit, because we have not made visiting it a priority. The horror is not in the cold or the dark or the scale. The horror is in the gap between what is there and what we are doing to learn about it. The horror is in the realized potential, the discoveries that will not happen, the models that will not be revised, the questions that will not be answered, because we are not sending enough spacecraft. We are the generation that knows the Kuiper Belt exists. We are the generation with the technology to study it. We are also the generation in which the gap between what we know and what we could know is widening, not narrowing, because the cost of sending spacecraft to the outer solar system is higher than most mission planners can sustain against competing priorities. This is uncomfortable. It is meant to be. Comfortable is the feeling you get when you look at the 8-planet diagram and think you understand the solar system. The discomfort is the beginning of understanding how much there is to learn. What is the Kuiper Belt actually asking of us? Not protection. It is not fragile. It has been sitting in the cold for 4-5 billion years and will continue for billions more. Not admiration. It does not register attention. It processes no awareness of being observed. What the Kuiper Belt is asking, to the extent that a region of space can be said to ask anything, is this: that we take our own curiosity seriously, that we match our ambition to the scale of what we are actually living in, that we are honest about the fact that the map is incomplete, that we know it is incomplete, and that we have the means to complete more of it than we currently choose to. We live in a solar system that extends to 100,000 astronomical units. We have explored a thin region around one small star, primarily within 50 AU, with most of our attention concentrated within the first 2 AU. We have been doing this for about 70 years, since the first artificial satellites. In cosmic time, we have just arrived. We are in the first moments of understanding where we live. In those first moments, we have found unexpected oceans under ice on Pluto and possibly other outer solar system worlds, a record of gentle, non-violent planetesimal formation in the shape of Arakoth, evidence of more material beyond the supposed edge of the belt, evidence of a possibly unexplained orbital clustering in the outer reaches, a cliff at 50 AU that no current model cleanly explains, and the knowledge that every time we look carefully at a place we have not looked before, we find something our models did not tell us was there. In those first moments, now think about what the next 70 years of outer solar system exploration might reveal, if we sustain the commitment to it, if we fund the missions, if we train the scientists, if we build the instruments, if we accept that some investments take decades to pay off and make them anyway. The Vera Rubin Observatory will find tens of thousands of new Kuiper Belt objects. Some of them will be in orbital configurations that no current model predicts. Some of them will be at distances where we did not expect to find anything. The census of the outer solar system will expand dramatically within the next decade from telescopic observation alone. And when we eventually send more spacecraft, and eventually we will, they will find things that Vera Rubin cannot see. The geology, the internal structure, the chemistry of the surface, the presence or absence of activity. The things that only a close look reveals. Every close look we have ever taken at the outer solar system has returned something unexpected. Everyone. The frontier is not a romantic concept. It is a description of a real situation. We live in a solar system, most of which we have not seen clearly. The Kuiper Belt is the largest nearby example of that unseen territory. And what happens there? The comets it sends inward, the material it has delivered to the inner solar system over billions of years, the story it holds of how everything began, is not separate from us. It is the context in which we exist, and perhaps the deepest thing to hold on to as you settle into this evening is this: the darkness beyond Neptune is not empty, the cold is not absence, the silence is not stillness, it is patient, and it is full in ways we have only begun to measure in an outer solar system that has not yet finished showing us what it contains. In a solar system that extends so far beyond the diagram that the diagram barely deserves the name, we are early. We are so early, and that means there is so much still. Here is an implication that almost never gets mentioned in discussions of the Kuiper Belt. Consider how the solar system formed. 6 billion years ago, a cloud of gas and dust collapsed under its own gravity. As it collapsed, it spun. The spin caused it to flatten into a disk. At the center, the pressure and temperature rose until nuclear fusion began. The sun ignited. In the disk around it, material began to clump together. Smaller clumps merged into larger ones. Over millions of years, the planets formed. But not all of the material ended up in planets. The outer solar system, far from the sun's warmth, retained material that the inner solar system processed and reworked. In the Kuiper Belt, objects formed from this primordial material and have been preserved there, in the cold, nearly unchanged since the solar system's first few million years. Now here is the implication. The material that formed Earth, including the material that eventually became you, was not static. It was redistributed. Comets from the Kuiper Belt fell toward the inner solar system throughout Earth's history. They delivered water. They delivered organic molecules. They delivered complex carbon compounds. The degree to which this cometary delivery contributed to Earth's current water budget and organic chemistry is actively debated, but the lower bound of that contribution is not zero. Cometary material reached Earth. Some of it contributed to the conditions that eventually supported life. The atoms in your body have a history. Carbon atoms that formed in stellar interiors billions of years ago. Oxygen atoms similarly ancient. Hydrogen atoms that may have been formed in the Big Bang itself. These atoms have been part of many different structures over the history of the universe. Some of them, at some point in the 5 billion year history of the solar system, may have been part of a Kuiper Belt object, part of a comet that fell inward when Neptune nudged it out of its stable orbit, part of the cometary material that contributed to Earth's chemistry. This is not certain. The fraction of your atoms that came this route is unknown and probably small. But it is not zero. You are, in a very loose but not entirely fanciful sense, partly made of the outer solar system. The boundary between the Kuiper Belt and Earth is not a wall. It is a permeable membrane that comets have been crossing for 5 billion years. The outer solar system has been reaching inward, quietly, the entire time life has been developing on this planet. When you look up at the night sky and cannot see the Kuiper Belt, because it is too dark and too distant for the naked eye, you are looking at something that has shaped you, not through any mystical connection, through physics, through the simple fact that comets fall inward and cometary material reaches planets, and some of that material eventually ends up in you. The Kuiper Belt is not separate from us. We are downstream of it. Here is why the discovery at Arrokoth matters far beyond the outer solar system. Before New Horizons flew past Arrokoth on January 1, 2019, the dominant model of how planetesimals form, the building blocks of planets, was called pebble accretion, or the hit and stick model. Objects grow by collision. Small things hit each other and stick. The combined object is larger and has more gravity. It attracts more objects. Over millions of years, small planetesimals grow into large ones, which grow into planetary embryos, which grow into planets. This model had problems. It predicted that growing planetesimals should be heavily cratered, bearing the scars of the collisions that built them. It predicted irregular shapes from violent mergers. It predicted a certain distribution of sizes in the outer solar system. Arrokoth was smooth, almost unscraped. Its two lobes were joined at a gentle seam with no impact evidence. Its shape suggested the two lobes had come together slowly at low relative speed. Not a collision, a drift. The favored explanation, gravitational instability, proposes that a cloud of pebble-sized material that is slightly denser than its surroundings begins to collapse inward under its own weak gravity. The material spirals together over thousands of years, accumulating without high-speed impacts, assembling itself into a planetesimal through a process more like a slow squeeze than a violent crash. If this is how Arrokoth formed, and if Arrokoth is representative of how outer solar system planetesimals form generally, then the story of how the solar system was built is different from what we thought. Not just in the Kuiper Belt, everywhere. The building blocks of all the planets may have assembled through the same quiet process we found preserved in Arrokoth's shape. Sit with that for a moment. We sent one spacecraft to one contact binary in the outer solar system, had a few hours of close-up data, and the result revised the theory of planetary formation, a theory that had been developed over decades, tested against many observations, considered robust. Now extrapolate. There are hundreds of thousands of large objects in the Kuiper Belt. Every one of them is a data point. Every one of them carries information about how the solar system formed, preserved in its shape, its surface, its binary companions, its ring systems, its internal structure. We have looked carefully at two of them. What will the next one tell us? We do not know. That is the point. That is the gap. That is the frontier. Here is one more implication worth sitting with before we close. Beyond the Kuiper Belt, beyond even the possible second belt suggested by the dust data and the Subaru telescope discoveries, lies the Oort cloud, or rather, lies what we theorize to be the Oort cloud. We have never directly detected the Oort cloud. We infer its existence from the comets that come from it. Long-period comets, those with orbital periods of thousands or millions of years, enter the inner solar system from all directions, not just from the plane of the solar system where the Kuiper Belt sits. This tells us they come from a roughly spherical distribution of objects, not a disk. The Oort cloud is that spherical distribution, extending from roughly 2,000 AU to perhaps 100,000 AU from the Sun. 100,000 astronomical units. The Sun's nearest neighbour, Proxima Centauri, is at roughly 270,000 AU. The Oort cloud extends to within a few times the distance to the nearest star. The outer solar system is not small. It is almost incomprehensibly large, by any scale humans normally use to measure things. No spacecraft has visited the Oort cloud. No spacecraft currently in existence could reach it on a timescale that matters for science. Voyager 1, the most distant human-made object, is at roughly 63 AU as of 2026. The inner Oort cloud begins at 2000 AU. At Voyager's current speed, it would take roughly 300 years to reach the inner Oort cloud. We will not be sending a spacecraft to the Oort cloud in any near-term sense of that phrase. But the Oort cloud is where the long-period comets originate. The comets with orbital periods of thousands of years, some of them plunging inward on their first visit to the inner solar system in geological ages. When Comet Hale-Bopp blazed across Earth's sky in 1997, one of the brightest comets of the 20th century visible to the naked eye for 18 months. It had just made its first visit to the inner solar system in approximately 200 years. Its previous appearance in the inner solar system was during the early Bronze Age, before Egypt's Middle Kingdom, before the construction of Stonehenge was complete. Hale-Bopp came from the Oort cloud. The outer solar system is not just the Kuiper Belt. It is everything beyond the Kuiper Belt, extending to distances we cannot currently reach, containing structures we cannot currently directly observe, sending material inward on timescales that span human civilizations. We are inside this solar system. We formed inside it. We will live and die inside it. And we have explored a fraction of a percent of it. That is not a failure. It is a beginning. We have been doing systematic space exploration for less than a single human lifetime. The solar system has been sitting here for 5 billion years, patient as only ancient things can be patient, waiting for something inside it to develop instruments sensitive enough to begin to see it clearly. We are that something, and we are, in every sense that matters, just getting started. Here is a practical example that brings the Kuiper Belt's comet delivery story into your daily life. You use GPS. Almost certainly, you use it regularly. For navigation, for location services on your phone, for the apps that tell you where you are. GPS works by receiving signals from satellites orbiting Earth at about 20,000 kilometers altitude. The satellites transmit signals with precise timestamps. Your receiver calculates how long each signal took to arrive, and from those travel times, it calculates your position. The precision required for this to work is extraordinary. The satellite's clocks must be accurate to within nanoseconds. The signals must be processed with extraordinary mathematical precision. Engineers who designed the system had to account for Einstein's theory of general relativity, the fact that time passes slightly faster at the altitude of the satellites than at Earth's surface, because they are slightly further from Earth's gravitational field. Without accounting for relativity, GPS would drift by several kilometers per day. What does this have to do with the Kuiper Belt? Your GPS works only if Earth has liquid water. The satellites triangulate your position on a planet that has a thin liquid water layer on its surface and in the atmosphere. GPS signals pass through water vapor in the atmosphere and are subtly affected by it. The entire system is calibrated for a planet with liquid water. Where did Earth's liquid water come from? Part of the answer, how large a part is debated, is comets. Comets that fell toward Earth during the early solar system, delivering water ice that melted into the oceans. Comets that originated in the Kuiper Belt and the scattered disk, nudged inward by Neptune's gravity over millions of years. The cometary delivery of water to Earth is not the only source of Earth's water. Some of it came from water-bearing asteroids. Some may have been present in the material that formed Earth directly. The exact contribution of comets from the Kuiper Belt is an open research question, but it is a non-zero contribution. Kuiper Belt comets contributed to the conditions that make Earth habitable. The GPS in your pocket is calculating your position on a planet partly shaped by the outer solar system. The map you use to navigate your city is running on infrastructure that would not work without water delivered, at least in part, by comets from the Kuiper Belt. This is what it means to say the outer solar system is not separate from us. The separation is not physical, it is only distance. The Kuiper Belt has been interacting with the inner solar system since the solar system formed, through the slow mechanism of orbital perturbation and cometary delivery. Everything here has been shaped, at least in part, by everything out there. We are not outside the outer solar system looking in. We are inside the same solar system, connected to it, downstream from it, made partly from the material it has sent inward over billions of years. Here is a pattern worth naming before we close. In 1846, astronomers discovered Neptune by predicting its location mathematically from its gravitational influence on Uranus. They pointed a telescope at the predicted location and found the planet. Prediction confirmed by observation. This was considered one of the great triumphs of Newtonian mechanics. The solar system was knowable. The equations worked. Mathematics could reach further than any telescope. In 1930, Clyde Tombaugh found Pluto at Lowell Observatory while searching for a hypothetical planet X. The discovery confirmed what astronomers expected: a planet beyond Neptune. It fit the story. In 1992, Jewitt and Liu found 1992 QB1 after 5 years of systematic searching. The discovery confirmed decades of theoretical prediction. It fit the story. In 2005, Mike Brown found Eris, larger than Pluto. This did not fit the story. The story said Pluto was the lone outlier. Eris revealed that Pluto was just the most famous member of a population. The story had to change. In 2015, New Horizons reached Pluto. Mountains, glaciers, a possible liquid ocean, active geology. Almost nothing fit the story. The story had to change again. In 2019, New Horizons reached Arakoth. Smooth surface, gentle formation. The story of how planetesimals form had to change. In 2024, New Horizons dust counter and the Subaru telescope survey revealed evidence beyond the supposed edge of the belt. The story about where the belt ends had to change. See the pattern. Every time we have moved from theoretical prediction to direct observation in the outer solar system, the story has changed. Sometimes the change is incremental. Sometimes it is fundamental. But the direction of the change is consistent. Reality is more varied, more complex, more active, and more surprising than the theoretical models predicted. This is not a failure of the models. The models are built from the best available data. The problem is that the available data is sparse. The outer solar system has been observed primarily through telescopes, from a distance, with limited resolution. The models built from that data are the best we can do with what we have. But every time we get close, every time we send a spacecraft and look directly, the models turn out to have missed something. The pattern is strong enough that it is not really a prediction anymore. It is an expectation. Go somewhere new in the outer solar system. Look carefully. Find something your models did not tell you was there. Every large Kuiper Belt object we visit carefully will surprise us in some way. We can be nearly certain of this, based on the track record of every outer solar system mission ever flown. The only question is which surprises we will choose to find, and when, and at what cost, and whether the generation making those choices understands what is at stake. We know enough about the Kuiper Belt to know we do not know enough about the Kuiper Belt. We know enough about the pattern of outer solar system discovery to know that we are missing things. We know enough about the timescales of outer solar system exploration to know that the decisions made in the next decade will determine what we know in the 2040s and 2050s. This generation is making those decisions now, in budget rooms and agency planning offices and scientific priority committees. Mostly without public attention. Mostly without anyone outside the planetary science community being aware that the decisions are being made at all. The Kuiper Belt does not care. It will be there, patient, in its billions of orbits, regardless of what we decide. The only thing that changes is how much we know about it, and how much of its story, our story, the solar system story, we will have learned by the time the next generation picks up the question. Here is a final thought worth sitting with tonight. Every generation of astronomers has inherited an incomplete map and left a slightly more complete one. Copernicus made it heliocentric, Galileo added moons, Newton explained orbits, Herschel discovered Uranus, Adams and Leverrier predicted Neptune, Tombaugh found Pluto, Jewitt and Louis found the Kuiper Belt. Stern and the New Horizons team found what Pluto actually looks like. Each generation added to the map. Each generation left the map more complete than they found it. We are a generation of astronomers and scientists and curious people who know the Kuiper Belt exists. We know it is large and populated and scientifically irreplaceable. We know it has been shaped by forces we do not fully understand. We know it has been shaping the inner solar system throughout the history of life on Earth. We know that every object we look at carefully is different from what we predicted. What we add to the map in the next 30 years is partly a choice. It will depend on the missions that get funded, the telescopes that get built, the scientists that get trained, the institutions that sustain attention on the outer solar system long enough to send something and wait for it to arrive. The Kuiper Belt will not ask us to explore it. It never has. It waited 5 billion years before Jewitt and Lou pointed a telescope at the right patch of sky in 1992. It waited 23 more years for New Horizons to arrive. It will wait however much longer we ask it to wait. But what we learn, and what we pass on to the generation after us, depends on what we do now. The decisions being made today will determine the state of the map in 2050. The proposals being written today will determine whether something is flying towards the outer Kuiper Belt in 2030 or 2040, or not at all. The institutional choices being made today will determine whether the pattern of discovery continues, whether the next flyby adds to the long list of things reality turned out to be different from what the models predicted. The universe is patient. We are not required to be. But the outer solar system rewards patience more than almost any other area of human exploration. The patience to propose a mission, the patience to wait for funding, the patience to wait 9 years for the spacecraft to arrive, the patience to wait 16 months for the data to transmit back, the patience to spend a career on questions that will not be fully resolved in that career. That kind of patience is not passive, it is active. It is the sustained decision, renewed every year, to keep the outer solar system on the priority list, to keep training scientists who care about it, to keep building instruments that can reach it, to keep accepting that some returns on investment come slowly. The darkness beyond Neptune is full, the cold is not empty, the silence is not stillness. It is patient. And so must we be. A like or a subscribe tonight, if this walk through the outer solar system was worth your evening, is one small way of saying that this kind of exploration matters, that the patience is worth it, that the darkness beyond Neptune deserves our attention. It helps this channel keep going, and it has been waiting a long time, long enough perhaps that even our slowest progress feels like Here is the honest accounting. As of 2026, we have catalogued roughly 3,000 Kuiper Belt objects with confirmed orbits. Estimates based on survey completeness and size distributions suggest there are hundreds of thousands of objects larger than 100 kilometers in diameter in the main belt region. Add the possible population beyond 50 AU suggested by the 2024 evidence, and the number grows further. Of those hundreds of thousands of large objects, we have looked closely at two out of hundreds of thousands. To put this in perspective, imagine you are an archaeologist hired to study an ancient city. The city covers an area of roughly 100 square kilometers. It is known to contain hundreds of thousands of structures. You have been given the resources to walk carefully through two of them. You have done so. Both were extraordinary. One contained an active heating system and water supply nobody expected. The other contained architectural techniques that rewrote the theory of how the city was built. You were given no resources to visit any others. You would write a report that said, "This city is far more complex than we thought, and we have barely begun to understand it." That is the state of Kuiper Belt science. We have written the report. We know the city is more complex than we thought. We have barely begun to understand it, and we do not have a confirmed next mission. There are roughly 400 years of work waiting in the Kuiper Belt. 400 years, at the rate we are currently exploring it. Even with dramatic acceleration, even with a sustained program of Kuiper Belt missions, we are looking at decades before we have a comprehensive picture of even the belt's main region, let alone the possible structures beyond 50 AU. This is not pessimism. It is an honest assessment of scale. The Kuiper Belt is large. Exploration takes time. We are early. But being early means the choices we make now matter more, not less. The institutions we build now, the missions we fund now, the scientists we train now. These are the inputs to the exploration that will happen over the next century. The map that the 22nd century will inherit from us depends on what we choose to add to it in the 21st. That is the responsibility of being the first generation to know the Kuiper Belt exists. Not just to know it exists, to decide what to do with that knowledge. The Kuiper Belt will still be there in 1,000 years. Some of the questions we are not answering now will be answered then. But some of the things we might learn now, from objects that are accessible to current technology with data that would fit into current models and advance current science, those things will wait, not because waiting is necessary, because we have not chosen to go yet. The darkness beyond Neptune is full of things we do not yet know. The silence out there is not emptiness. It is the silence of things that have been waiting to be found since before the Earth had oceans. We are early. There is so much still. And here is what remains true, regardless of how long we wait. Every object in the Kuiper Belt has been exactly where it is for 5 billion years. Not moving far, not changing significantly. Orbiting slowly, in the dark, in the cold, in the silence that has no name in any human language because no human has ever experienced it. These objects do not know they are being observed. They do not know they had been catalogued. They do not know that one spacecraft flew past two of them and changed what we thought we knew about how the solar system formed. They are simply there. And we are here. On a small warm planet, 93 million miles from a medium-sized star, in the inner zone of a solar system that extends to distances we have not fully mapped, on a geological timescale that has barely registered our existence. We have been systematically studying the cosmos for less than a century. We have been sending spacecraft beyond our planet for less than 70 years. We have been visiting the outer solar system since 1972, when Pioneer 10 became the first spacecraft to pass through the asteroid belt and head toward Jupiter. In that time, we have learned more about the solar system than in all of previous human history combined. And we have barely started. The Kuiper Belt is not the end of the story. It is one of the first chapters of a story we are only beginning to read. The rest of the story, the Oort cloud, the scattered disks' full extent, the possible structures beyond 50 AU, the question of Planet 9, the thousands of dwarf planets we have not yet found. That story will be read by people who have not yet been born using instruments that have not yet been designed, asking questions that we do not yet know to ask. That is not a sad thought. It is a magnificent one. The frontier is not closing. It is opening. Every discovery we make reveals more of what we do not know. Every mission we send returns data that generates new questions. The solar system is not becoming more familiar with exploration. It is becoming more strange, more complex, more varied, more interesting. Every close look reveals a world more sophisticated than the model predicted. The darkness beyond Neptune is not empty. The cold is not absence. The silence is not stillness. It is patient. It is full. And it is waiting for us to look more carefully. We are so early, and that means there is so much still.